Hi everyone, my name is Rituja and welcome back to Data to Crunch. So right now we are at the initial stage of learning Spark and Databricks where we are trying to cover some important theoretical points. So now let's dive in and start crunching some concepts together. So today we will be diving into some of the most important concepts in Apache Spark. So this is how our agenda looks like. Firstly, we'll see about the lazy evaluation. That means how Spark optimizes the computation by deferring its execution until an action is triggered. Then we will see fault tolerance with Lineage, where we will try to understand how this Spark ensures data reliability via RDDs. Then we will try to understand the concept of directed acyclic graph, followed by how this narrow versus wide transformation works. Then we will try to see Catalyst Optimizer and Tungsten Execution Engine, followed by Catalyst Optimizer in SparkSQL, where we will try to understand how this Catalyst handles both logical and physical query planning. And lastly, we will see one example which will cover all the concepts which are going to cover today via one example. So now let's get started. Now let's see about the lazy evaluation concept. So lazy evaluation is a crucial concept in Apache Spark that ensures efficient data processing. So unlike other traditional systems where transformations are executed immediately, Spark delays its execution until it is absolutely necessary. So this approach of Spark allows it to optimize its operation and reduce the resource consumption. So if we'll see how it works, then we can say that if you are applying transformations like map, filter, or flat map to an RDD or data frame, Spark doesn't immediately execute these operations. So instead, it just records the transformations into directed acyclic graph. So this DAG is a logical representation of all the steps and operations that are to be performed on the data. For example, suppose you apply multiple transformations such as filtering or mapping to your data, then Spark will not execute these operations right away. So instead, it will just build a DAG to keep the track of all the operations that are to be performed on your data. So this allows the Spark to analyze and optimize the sequence of transformations before the execution. So it also allows the optimization before execution. That means Spark analyzes the entire computational workflow. So it looks for the way to optimize the plan, such as maybe combining multiple transformations into single stage. So this helps the Spark to reduce the unnecessary data shuffling across the clusters, and it will automatically speed up the overall execution. So suppose for instance, if you are applying a series of filters or map one after another on your data, then Spark might combine them into one stage to avoid the cost of processing intermediate data more than once. So this way it can minimize the redundant operations and optimize the data movement across the node. Then the next one we can say is action triggers execution. That means the actual execution of transformation happens only when an action is triggered. So actions like collect, count, or save, and so on cause the Spark to evaluate the DAG and begin the processing of the data. Until then, Spark only builds the DAG without performing any actual computation. So suppose for example, if you are performing a series of transformations like filtering or mapping on your data, then Spark will not execute it immediately until you call an action. So suppose if you are requesting the result with the collect function, then at that point Spark will go through this entire DAG. It will optimize the performance before the execution, and afterwards it will execute the transformations in the most efficient order, and then it will return the result. Okay, so now let's see about the benefits of it. So the first one we can say is optimized performance only. So lazy evaluation, it allows the Spark to optimize the execution plan before actual processing of data happens. So by combining and reordering the transformation, Spark will reduce the unnecessary computation and it will minimize the time that will get spent on data shuffling, which will lead to a faster performance. Then the next one we can say is resource efficiency. So since the transformations are only executed when needed, Spark avoids the wasting memory or computational power on intermediate result. So this makes it highly resource efficient, especially when we are working with the large data sets. Then the next one we can say is fault tolerance. So in the event of failure, Spark can use the DAG to recompute the loss data based on its lineage. So it will not need to process the entire data set again. So this will ensure the fault tolerance while maintaining its best performance. Then the last one we can say is avoiding materialization. So with lazy evaluation, intermediate datasets are not materialized in the memory unless necessary. So this saves the memory and computation time since Spark doesn't need to store every intermediate result during the transformation operations. So along with the advantages, it also comes with the disadvantages. So the first disadvantage could be delayed execution. So while lazy evaluation improves the performance, it can sometimes make this debugging more difficult. So since these operations are only executed when an action is triggered, errors only surface at that point, which can make it challenging to trace back the original issue. Another disadvantage would be overhead of building DAG. So for simpler or smaller tasks, the overhead of building and optimizing DAG might outweigh the benefits of lazy evaluation, making it less efficient in certain scenarios. So in conclusion, we can say that this lazy evaluation concept is an essential feature in Apache Spark, which allows efficient data processing. So by deferring the execution until an action is triggered and optimizing the execution plan before running the operation, Spark ensures that only necessary computations are to be performed. So this approach not only enhances the performance but also optimizes the use of resources, making the Spark an ideal choice for handling the large scale data processing tasks. Now let's try to understand the concept fault tolerance with Lineage. So one of the Apache Spark's standout feature is fault tolerance, which is mainly achieved through Lineage. So when you apply transformations on your data, whether it's RDD, data frame, or dataset, Spark constructs a lineage graph. So this graph keeps the track of all the operations that are to be performed on the dataset by creating a record of logical transformations that have been applied. So it acts like a recipe of how this data was derived, which is a crucial for fault tolerance. So suppose if in the case of failures such as maybe node crashing or data partition being lost, Spark does not need to recompute the entire dataset. So instead, it uses this lineage graph to recalculate the only affected partitions. For example, imagine you have a large dataset and you apply filter transformation. So if one of the partition of this filtered datasets become unavailable, Spark will reapply this filter transformation on the original dataset to restore the only lost partition rather than reprocessing the entire dataset. So this approach minimizes the amount of recomputation needed by ensuring that data processing continues smoothly even in the case of failure. So this fault tolerance mechanism makes the Spark highly reliable, especially for the large scale distributed computations where failures are inevitable. So why is this lineage important? So this lineage is important for efficiency because it reduces the unnecessary recomputations by recalculating only what is necessary. Then the next we can say scalability because it supports the large scale data processing while handling the node failures seamlessly. Then we can say resilience because it ensures that Spark jobs can continue processing even if the part of the data or infrastructure fails. So now let's try to understand this concept by one example. So consider a scenario where dataset undergoes multiple transformations like filtering out the invalid rows, then performing a map operation to transform the data. And if a partition fails after the filtering step but before mapping step, then Spark will use this lineage information to go back to the original data and it will reapply the filter operation on that specific partition by avoiding the need to reprocess the entire dataset. So by leveraging this lineage, Spark ensures data integrity and efficient recovery from failures, making it ideal solution for fault tolerance, large-scale distributed data processing tasks. Now let's try to understand the concept of directed acyclic graph. So in Apache Spark, this DAG is a way of organizing operations that need to be performed on your data. So each operation is represented as a node in the graph, and the arrows between these nodes shows the order in which these operations need to happen. So this term cyclic means there are no loops. So once this operation is performed, it doesn't go back to the previous one. So when you run a Spark job, Spark creates this DAG to plan how the operation should be executed. So this helps the Spark to figure out the most efficient way to do this work. For example, if it also can decide which operations can run in parallel, which will save both time and the resources. So by organizing the tasks into a DAG, Spark ensures that the operations are completed in the correct order. Now, when you use actions in the Spark, which may be like collect, count, or save, it triggers the execution of the DAG. So Spark doesn't immediately start the work when you call these transformations like map, filter. Instead, it just builds this DAG of the tasks. And when you call these actions, Spark looks at this DAG and it start running the tasks in the best order. So one of the key benefits using this DAG is optimized execution. So Spark can run some tasks in parallel also. For example, if you are filtering out the data in different partitions, Spark can run these operations at the same time because they don't really rely on each other. However, when the tasks like group by, it requires reshuffling of the data across the partitions, Spark organizes those steps into separate stages. So this way Spark reduces the time consuming operations like moving the data around and then performs the task in the most efficient way. So the next concept is DAG scheduler. So DAG scheduler plays an important role in this process because it breaks the DAG into different smaller stages based on the task that need to shuffle the data. So the scheduler ensures that these stages are executed in the right order. If the task can run in parallel, it does so, making it the best use of available resources. So if a task fails, DAG scheduler only retires the failed task, not the entire stage, which makes the job more efficient. Then DAG visualizations come into scenario. This DAG visualization, it allows you to see this DAG structure. So basically it's a graphical way of showing the tasks and their dependencies. So with this visualization, you can easily see the flow of operations, then what tasks depend on each other and where you might face the delays or the bottlenecks. So basically this visualization is helpful for understanding the job better, optimizing its better performance, and it also helps in troubleshooting if something goes wrong. To sum up, we can say that this DAG in Apache Spark is a powerful way to plan and optimize the operations on the data. And the DAG scheduler, it ensures the tasks are executed in the right way and it retires only the failed tasks. And lastly, DAG visualization, it makes it easy to see and understand how these tasks are related. And optimized execution ensures the Spark performs this task very efficiently by minimizing the expensive operations and using these resources efficiently. So let's try to understand this concept by looking at this example of e-commerce order processing. Now let's imagine a real world business scenario to understand these concepts of DAG, optimized execution, and DAG scheduler, how they work together in Apache Spark. So now we have one e-commerce company that needs to process the customer orders efficiently to generate sales reports and the personalized product recommendations. So first business needs to extract the data that involves that getting data about the customer orders from the database. Then we need to remove any error or inconsistencies if that are present in the order data. That means we need to clean the data, and afterwards we need to generate sales report that indicates summarizing total sales, popular products, and customer demographics. And based on the clean data, we need to suggest the products to the customers based on their buying history. And lastly, we need to merge both sales reports and product recommendations to get the final report. Now let's see how this Apache helps in this process. So the first one is DAG creation. So Spark creates this DAG to represent the sequence of operations involved in this process. Each task, such as extracting data, cleaning data, generating sales reports, and so on, these are represented as a node in the DAG. So the arrows between these DAG, it indicates the order of execution, which shows that which task is dependent on which. For example, data extraction must be completed before data cleaning. Then data cleaning needs to be performed first in order to get the sales report and the product recommendation, and so on. So for this DAG creation, we can look for optimized execution also, if there is any another way to process this data efficiently. So in this optimized execution, Spark looks at the DAG and decides the best way to execute these tasks. So independent tasks can be run in parallel to save the time in this optimized execution. For example, generating sales report and then recommending the products. These both are independent of each other. So they can be run at the same time because they don't really depend on each other. So this parallel execution helps to speed up the process. On the other hand, we can say that this generates sales report and product recommendations. These are dependent on the clean data. So we need to wait for the data cleaning process to get completed first for these two steps. Once both sales generation and product recommendation are done, Spark can combine these both the nodes to get the final report. So this parallel execution, it reduces the total time needed to complete the workflow by ensuring that resources are used very efficiently. So how come DAG scheduler comes into this scenario? So DAG scheduler is responsible for executing the task in this DAG. So it must break the DAG into smaller stages and it needs to schedule the task based on their dependencies. For example, it will schedule the data extraction first, then data cleaning, and after that it can schedule both sales report generation and product recommendation parallel. So this scheduler ensures that these tasks are executed in right order, that are independent tasks can run at the same time. So if any task fails in this scenario, for instance, data extraction task fails, then task scheduler will only retry that failed task and not the entire set of operations. So which will help to save the time and the resources. So this ability to retry the failed task ensures that the system is efficient even when this error occurs. And finally, at the end, this will be our DAG visualization, which is nothing but a graphical way to represent the sequence of operations in the Spark. So in our example, the first step would be extracting the data. Once this extraction is completed, it will give the output to clean the data. This node of cleaning the data will clean the data, and once it's completed, it will provide its output to both the nodes, which are generate sales report and product recommendations. So these both the nodes will run in parallel and will generate the output. And once this output is generated from both the nodes, that will be treated as an input to the final report. And final report will provide both sales report and the recommended products at the end. So this visualization will at the end help in understanding the workflow and identifying the potential bottleneck. So if this sales report generation is taking long time, we can see in the DAG and consider optimizing that specific part in that workflow. So in conclusion, we can say that in this e-commerce example, Spark uses the DAG to manage and optimize the order in a processing workflow. The DAG ensures that operations are executed in a correct order with parallel execution of independent tasks to save the time. Then the DAG scheduler ensures that tasks are executed efficiently and it retires only failed tasks by optimizing the use of resources. And finally, this DAG visualization, it provides a clear view of the workflow, making it easier to understand, monitor, and optimize the process. So by using this Apache Spark DAG structure, e-commerce business can efficiently process large amount of data and then generate the reports and then afterwards can offer the personalized recommendation by saving the time and the resources both. In Apache Spark, these transformations are categorized into two types based on how they handle the data processing. And those types are narrow transformation and then wide transformation. So both the types are crucial for building efficient distributed data processing pipeline, but they differ in their approach to the data distribution and execution. So the first one is narrow transformation. So a narrow transformation occurs when the output of transformation in Spark is determined by the data within the single partition. So in other words, we can say that each input partition produces exactly one output partition, which means there is no data shuffling or the movement of data across the nodes. So this makes the narrow transformation highly efficient since they can be executed in parallel across the partition without incurring the overhead of transforming data between the nodes. So common narrow transformations include operations like map, filter, and flat map, which transforms the data locally within each partition. Since these narrow transformations do not require shuffling, they are typically faster and less resource intensive. For example, if you perform a filter transformation to select the transactions above $100 in a dataset, Spark will filter the data within each partition independently. So there is no need for the data to be moved between different partitions, making this operation faster. So the next one is wide transformation. So in contrast, this wide transformation involves the operation that require data from multiple partitions that need to be combined or redistributed. So these transformations typically necessitate data shuffling, which means data from one partition is moved to another partition to complete the operation. So operations such as group by key, reduce by key, and join are the wide transformations because they require elements from different partitions to be grouped together for the aggregation or joining. So shuffling can introduce significant performance overhead due to the cost of transferring large dataset of the data across the network and potential for disk I/O. For instance, if you perform group by transformation to aggregate the transactions by product category, Spark needs to shuffle that data across the partitions to ensure that all the transactions for the same category end up in the same partition. So this process involves sorting or moving of the data, which can be resource intensive, especially when you are working with a large data set. So the main difference between narrow and wide transformation lies in the data processing model only. These narrow transformations are efficient and parallelizable because they work within a single partition without requiring the data movement across the partitions. So this makes them faster and more scalable. While on the other hand, wide transformations are more computationally expensive because they require data shuffling and this increase in execution time and it can lead to performance bottlenecks, especially in the large scale data processing tasks. So Spark breaks this DAG into stages by strategically organizing the work, and those are Catalyst, Optimizer, and Tungsten Execution Engine. So these are the key components that work together to optimize and execute the queries efficiently. So if we talk about the role of Catalyst Optimizer, so it is a part of Spark SQL engine and is mainly responsible for optimizing the queries at the logical level. So the Catalyst Optimizer, it applies the series of rule-based transformations to a logical plan of a query to make it more efficient. So this includes optimizing the query structure and simplifying the logical query before the physical execution. So the key components are the first one is logical plan, which is nothing but the initial plan representing the SQL query in the logical form. Then logical optimization, it transforms the logical plan to improve the query efficiency, such as removing redundant operations and so on. And lastly, physical plan generation converts the logical plan into one or more physical plans by representing different strategies for the executing queries. Once this Catalyst Optimizer is done, then Tungsten Execution Engine comes into scenario. So this engine is responsible for the physical execution optimizations and the code generations. So it works on a physical plan produced by the Catalyst to further improve the query execution performance at the hardware level. So the key component the first one is physical plan, which is nothing but the plan for how to execute the query on physical resources, for example nodes in the Spark cluster. Then in the physical optimization, Tungsten applies the optimizations to improve how Spark manages the memory, CPU, and data movement for the physical operations such as off-heap memory management and memory caching. And then the code generation. So this code generation, it in this Spark generates the bytecode for specific operation to reduce the overhead of the functional calls to make this execution faster. So if we see the overall process, the first one is when the query is submitted, Spark first translates it into a physical logical plan. Then Catalyst Optimizer applies various logical operations and then various logical transformations and optimizations on this plan. And once these logical optimizations are applied, then physical plan gets generated. Then the Tungsten execution engine takes over for low level optimizations like memory management and code generation. And finally, the query is executed using the optimized physical plan. So in Spark, the combination of this both Catalyst Optimizer and Tungsten engine, it ensures that queries are processed in the most efficient manner, both at the logical and physical levels. Now that we understood the role of Catalyst and Tungsten in Spark, now let's dive deeper into how your query is translated into an efficient execution plan step by step. So this transformation begins with Spark's ability to break a query into logical, then optimized logical and physical plans by ensuring unparalleled query execution efficiency. So the journey of your query in Spark starts as an unresolved logical plan, which is essentially a raw blueprint of a query without any validations. So with the help of schema catalog and the analysis rule, Spark resolves this into a valid logical plan. But Spark doesn't stop there. Through optimization rules like predicate pushdown or filter reordering, it redefines this into an optimized logical plan, which in short, this plan, it aims to reduce the resource consumption and speeds up the computation. So at this point, Spark generates multiple physical plans. So each plan represents different strategies to execute the query. But which one should the Spark choose? So enter the cost model. So this cost model is a critical component of Catalyst, which evaluates each physical plan based on the execution efficiency, and then it picks up the best one for the execution. So with the optimal physical plan selected, it's time to hand over this REN to a Spark's Tungsten execution engine. So this is where the real magic happens. So the Tungsten converts the plan into low-level bytecode by enabling the efficient memory usage and blazing the fast computation. So once this Tungsten execution engine compiles the selected physical plan into executable tasks, Spark orchestrates their execution using its distributed RDD models. So this synergy between logical plans, Catalyst, and the Tungsten engine, it ensures that Spark performs at its best, regardless of the workload complexity. Now let's try to understand one example of customer transaction analysis. So here, suppose you're working with a data set which contains millions of customer transactions and you need to filter the purchases which are over $1,000. Then you need to group that result by product category, and afterwards, finally, you need to write the aggregated results to an external storage system. So the first concept which we have learned is lazy evaluation. So when you apply the transformations like filter to extract the transactions which are over $1,000 and then the group by to group the transactions by product category, Spark doesn't perform these operations immediately. Instead, it just builds a DAG that represents logical plan of these operations, deferring the execution until an action like write is called. Then the next concept is fault tolerance. So if a node in Spark cluster crashes while performing or processing the filtered transaction, then Spark uses the lineage graph to recompute the lost data. So it starts from the original datasets and it reapplies the filter transformation to recreate the missing partitions without reprocessing the entire dataset. Then the next concept is optimized execution by DAG. So when you trigger the write action to save the result into a storage, the Spark evaluates the DAG. So it processes the narrow transformation like filter in one stage and then executes the wide transformation, which is group by, into another stage by efficiently minimizing the data movement across the partitions. So Spark schedules the tasks to maximize the cluster resource usage, and it minimizes the costly operations like data shuffling by ensuring the faster execution. And that wraps up today's session on Apache Spark. So we have explored key concepts like lazy evaluation, fault tolerance with Lineage, then Spark's powerful optimization frameworks like Catalyst Optimizer and Tungsten Execution Engine. We also saw how this narrow and wide transformation works and also demonstrated a real world example of customer transaction analysis. So I hope these insights will help you to better understand the Spark's inner workings and how to leverage its features for optimized performance. So in the coming up next lecture, we will see how can we set up this Databricks account, and we will also have the overview of this Databricks platform. So if you have found this video helpful, then don't forget to like, share and subscribe for the more content. You can also drop your thoughts or the questions in the comment section below. I would love to hear that from you. And thanks for watching, and I'll see you in the next video.